Okay, let's start. Good morning. So this week, our main goal is to start talking about continuous functions. But we have some items remaining from last week, so I thought I didn't want to rush it. So what we're going to do is we're going to change the schedule just a little bit. Today and tomorrow, we're going to keep working on sequences because there are certain notions that are very useful. Certain convergence theorems we're going to discuss today, and tomorrow I would like to discuss these notions of limsup and liminf. And then instead of spending 6 days on, or 6 classes on continuity, we're going to spend 4 classes. Things are interconnected, of course, and it will be useful to study these convergence theorems and all that stuff. Are there any questions? Okay. Okay. So subsequences. So the notion of a subsequence we had defined on Friday, but let me just briefly remember or recall it. So for x bullet, right, a sequence, let's start at time 0. Taking values in some arbitrary set x, be a sequence, for x a sequence, a subsequence of x bullet is it's another sequence, let's say is x prime bullet, sequence that starts with the same time, such that for some strictly increasing function j from one time set to the other one, well, let me just write it like this. X prime bullet is the composition of x bullet with j. In other words, to figure out where your subsequence is at time n, you first apply to n this function, j of n gives you some other time, and then you plug that time into the original sequence. So we had talked about composition of relations, and composition of functions work pretty much the same way. But here's an exercise about this. If I have 3 sets, x, y, and z, a relation R from x to y, and yet another relation from S from y to z, then of course I can compose these two. S composed with R. That's a relation from x to z. The statement of the exercise is that if R really is the graph of some function f, and S is the graph of some other function g, then the composition of them, too, is the graph of some function, which I denoted by h there. But the typical notation for this is g, O, f. G composed with f, and this is also the same notation that I used here. Okay? How many of you have seen this notion before? Composition of one. Pretty much all of you. Yeah, so how do you figure this out? Well, you take a point, you take an x value, apply f to it, now you have a y value. Then you apply to that outcome g. Right? So h of x is g of f of x. And this notion of taking a subsequence literally is the same thing. Let's also talk about what it means for this function to be strictly increasing. Well, I want, for instance, j of 1 to be strictly greater than j of 0, and so on, right? So this means that for any n, this happens. The point here is that recall the heuristic was this. This is sort of like my strip of film, right? I have like different scenes, different frames. And to get a subsequence, what I do is I edit out certain frames. I don't get to shuffle the order of scenes, order of frames. What I can do is I can get rid of some of the scenes, okay? That's the idea behind a subsequence. So the temporality is the same direction. Any questions about this? So here's a simple example, of course. For instance, yeah. Let's take, well, x sub n to be minus 1 to the n. Well, I can take, for instance, j of n, my function, to be, let's say, 2n. Okay? Let me take even times. So x sub j of n defines a subsequence. So okay, plugging this in, this is x sub 2n, but then of course this is nothing but minus 1 to the 2n, which is just 1. So you see, this is an alternating series sequence, whereas this particular subsequence is a constant subsequence. Okay? And of course, I could have done other things. I could have taken sort of more complicated functions. Typically, what's going to happen is that when you're trying to prove things, you're going to try to come up with a certain subsequence, in other words, a certain strictly increasing function that is defined recursively. Like you're going to be using induction to get what you want ultimately. Okay? So you have a movie, you have some footage, let's say, and you're sort of editing out certain frames that you don't want to see. And that's going to produce some other behavior. Right? So if I start with this guy keeps alternating. So this is what happens. But by editing out these parts, I can just turn it into a constant sequence. Okay? So we're going to see this idea over and over again in this class. We're going to have a sequence, and we're going to want that sequence to behave a certain way, but alas, it's not going to behave that way. And then what we're going to do is we're going to edit out the behavior that we don't want. Of course, it's an art. It's an art to figure out what you should be editing out and all that. Okay. Any questions about these two? Okay, so let's start talking about now some convergence theorems. So the first one is what is called the monotone convergence theorem. Now, note that the notion of a subsequence, it's admissible for an arbitrary set, because I'm not really talking about convergences and blah, blah, blah. I could have taken a sequence and subsequences of it in a metric space, in which case I could have talked about convergence also. This particular one, this particular theorem, is about really sequences of real numbers, because you need some ordering. Okay, so. Let x bullet be a sequence of real numbers. If it is non-decreasing, so let me say this is part one. If x bullet is non-decreasing, and you can also see the word increasing. So aka increasing, aka So okay, so this is not necessarily strict. Could be constant. Constant sequences are non-decreasing or increasing, which is kind of confusing. Both of these terminologies are used, unfortunately, but it is one of these confusing things. Then I have some knowledge about what the limit is. Limit as n goes to infinity of x sub n is, well, supremum of its trail. Okay. Now, this, of course, is always non-empty, which means that this sup is never minus infinity, but it could be positive infinity. Okay. So it's really this. And I'm going to leave it to you as an exercise to really make sense of what it means for a sequence to have limit infinity. Okay? Sequence of real numbers. So this is also mentioned in the book, but it's nice to think about how to define these kind of things. Make sense of this guy. Okay. Now this statement in particular says that if x is non-decreasing and furthermore x, so the sequence is bounded from above, in other words, its trail is bounded from above, then its limit is the supremum, which is a finite number. Okay. And of course, a similar statement holds if it is non-increasing. So if x bullet is non-increasing, which means that it is decreasing, which means that the other way around holds. Decreasing. AKA, for all n, x sub n is greater than or equal to x sub n plus 1, then limit equals infimum. And again, this is not positive infinity because it's non-empty, it's a non-empty set, but it could be minus infinity. That's the statement. Okay. Yes?
So a constant sequence can be non-decreasing or non-increasing?
Yes, it is both. Exactly.
Okay, it is both.
Yes, this is like it's a silly thing. Like that's why I like to use this, and that's what they use in the textbook as well. But this is also very common.
Okay.
And so if a sequence is either one of these, you would call it monotone.
Okay.
Yeah. Monotone means either this or this. So this is not monotone. This is monotone. It's constant. In particular, it is monotone. Monotonous. Nothing that crazy happening. Okay. And why do we care about these kind of things? Because ultimately, given a sequence, which is sort of like a discrete time signal, it sort of like maybe records some information, some data, whatever. But we want to summarize it, okay? You don't want to be like, oh, this is a function, it depends on n, blah, blah, blah. You don't want to have that, okay? You can say, oh, here's the graph, but more complicated sequences have more complicated graphs. This, again, even though it gives an idea for simple sequences, more complicated sequences, it's not, for more complicated sequences, it's not as straightforward to just look at the graph and see what it's doing. So what you do is, you look at the asymptotic behavior. And the reason why this is a theorem is that it says that, oh, for specific types of sequences, the asymptotic behavior can be determined rather straightforwardly. Okay, you look at the trail, the max in a sense of that trail, not exactly max, but sup of that trail gives you the sort of the limits. Okay, so it's all about sort of summarizing the information that this particular sequence has. And like I said on Friday, saying that this limit, so the limit of this sequence is this number or extended number, on the one hand says that this limit can be approximated using x sub n's for large n, but often it's actually the other way around because the limit is supposed to be the summary. And once you have the limit, you get to say, oh, for large n, my x sub n, which is really what my data is all about, is approximately this thing. Okay? Any questions, any further questions about this? So let's prove it. So whenever you have a sequence, okay, first things first, you first need to have a candidate for a limit. You first have a limit, candidate limit, and then you figure out if that is indeed the limit, okay? So this theorem itself gives us the candidate. I'm not going to do the second part. I'm going to leave it as an exercise. It's pretty much the same argument. I'm just going to do the first part. So once you have the candidate, you can say, oh, it does converge or not. So let's do this. Let's separate the cases. You know, I like to separate cases. First of all, I need to figure out, I need to say something about whether or not this is a finite number. Either it is infinite or it's not. So proof of the first part, and the second part is going to be an exercise. And you see here's another instance of an important phenomenon. Often, when it comes to doing abstract math, figuring out what the statement of the theorem is sort of the hard part. Once you figure out the statement, the proof basically just follows from opening up the definitions. This is not always true, but in this case it is, I think. Okay, so because the theorem itself tells me what the candidate is. So either let me call this alpha so that I don't write it many times. So either alpha is infinity XOR alpha is a finite number. Okay, if alpha is infinity, by definition that means that the trail set, so the image of the function x bullet, is unbounded. So let's write it like this. So this is, let's say, case number 1. This is case number 2. Well, I guess now I have to do this exercise. What is this? How do you make sense of it? Well, infinity is supposed to be a point at infinity, right? And so if I were to open up the epsilon-delta definition, I would want to say something like, for any epsilon, there is some n such that after that n, x sub n is epsilon close to infinity. Okay? Really, instead of writing epsilon, because epsilon is supposed to be a small number, use some other letter. Let's say capital M. For arbitrarily large numbers, there's a time such that after this time, x sub n is, well, let me just write it like this. In fact, like this, perhaps. Okay, but this is by definition because I'm saying that this guy is unbounded. Okay, so this is as follows. Since x sub n varies over positive or non-negative integers is unbounded. From above in this case. From above. Okay. If you want, you can be more formal about it, but I don't think that is very important. The more important case is number 2. Okay. Now, first of all, so what I want is the following. For any epsilon, there's an n, such that for any n after capital N, x sub n minus alpha in absolute value is bounded by epsilon. Okay? Now, but I can do things about this here, because I know that by definition, alpha is the sup of this. In particular, that means that alpha is, it dominates any x sub n, which means that this absolute value literally is equal to alpha minus x sub n. This absolute value equals alpha minus x sub n. Okay. And so this clause I can rewrite as this part. Well, what can I do? I can send this x sub n to the other side and epsilon to this side and write it like this. Alpha minus epsilon is dominated strictly by x sub n. So this is what I want. For any epsilon, I want some n capital such that after that capital N, x sub n is greater than alpha minus epsilon. Of course, it is bounded from above by alpha because it's a supremum, but this is what I want for convergence. Okay. Well, by definition, alpha is a finite number. That's my case. And it's a sup of the trail. So given any epsilon, I know that alpha minus epsilon is not an upper bound. Which means, so, given epsilon, alpha minus epsilon is less than alpha, which is a supremum. So there is at least one point that I can inject between this and this, such that x sub n dominates strictly alpha minus epsilon. Any questions about this? I'm playing some games, but I'm just opening up the definition. Should I repeat this point? No? Okay. Well, if at n I have this, well, I know by definition that x bullet is non-decreasing, which means that for any lowercase n after uppercase n, I'm going to be not decreasing, which means that the same bound is going to hold. So, in other words, I was able to get for any epsilon sometime n, capital N, such that after that time, all my x sub n's fit into this. That's literally the definition of x bullet converging to alpha. Okay. So what are the tactics I'm using? I open up the definitions. Okay, I need to show that this limit equals this. I open it up. You don't need to write it using logic and stuff like that, but I would recommend writing it some way. So in the textbook, they use plain English and stuff like that. Obviously, that takes more time, but depending on your style. You open up the definitions, and you sort of slowly get closer and closer to it, okay? And for instance, as opposed to something like computer science, programming, you don't need to sort of argue in a linear fashion. You can just argue a little bit from the beginning, a little bit from the end. Ultimately, insofar as you can sort of build a possibly nonlinear or jumping around argument that connects the hypothesis to the conclusion, that's a valid proof, okay? So often it's good to start from the end, I would say. Any questions about this? Well, I was expecting you guys to have more questions about this. Are you being serious? Otherwise, I'm gonna speed up. So. Yes.
I maybe don't have specific questions because I'm not quite sure what to ask, but I'm just a little unclear on maybe just like the last part of that sentence.
From here? Yeah. So we want to verify this statement. So this first black statement was what I obtained by just literally opening up the definition. Now I started using the context. I said to myself, oh, alpha is always greater than or equal to this guy. So because I don't want to see the absolute value ultimately. Evaluating the absolute value is harder than evaluating something that doesn't have the absolute value. I'm trying to simplify it. So I get rid of it. And I'm saying, oh, how do I get rid of it? Well, if I were to try to erase these absolute values, well, because this is always greater than this, well, I need to flip the sign. So this absolute value is this. And then I manipulate it just a little bit more to get an expression that I've seen in the definition of the sup. So you see, so far, until the end of this point, we didn't use anything specific about alpha being the supremum. We just use the fact that this is an upper bound. Now I want to verify this. Because I want to verify for any epsilon there's blah, 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 I need to fix an epsilon. So given an epsilon, alpha minus epsilon, which is this number I have here, is a number, actual number, strictly less than this alpha. By definition, this alpha is a sup. So it's the best upper bound. So you cannot get any better, which means that this is not an upper bound. By definition, this being not an upper bound means that you cannot bound everything by this. So there's something that exceeds this, which means that there's some n. There's also some index management going on here, of course. But there's some n such that x sub capital N exceeds this guy. And now, finally, I use the hypothesis that x bullet is non-decreasing. I know that if I were to look at capital N plus 1, it cannot decrease. So I can only go up. Which means that for all but finitely many indices, x sub n is greater than alpha minus epsilon. But that was what I realized, that was what I wanted. And I'm done. Does this make sense a little bit? Okay. So you keep playing, you're going to keep playing this game over and over again. And in problem set 3 too, you're going to have a bunch of sequences and so on. If I'm saying if this converges, then that converges, or maybe the other way around and so on. You always keep playing these games. Any other questions? Okay. So here's an application of this, which is very nice. This is now basically monotone convergence theorem, but for subsets. Now, we didn't really talk about what it means for sequences to converge, so we're not going to need it. But what we're going to do is we're going to have, again, let's say, a monotone sequence, let's say, of intervals. if I have a decreasing sequence of closed and bounded intervals, I want to say something about their intersection. So let me write it down. This is what is called the nested interval property. There's a more general version of this, which is called the Cantor Intersection Theorem. So what is it? Property. It's a theorem, but you call it a property, I guess. Okay. Let me say I sub bullet be a sequence of closed and bounded intervals of the real line. Of R. Intervals of R, they're always defined as subsets of the real, so I'm just going to write it like this. If I bullet is decreasing, maybe I should say something about it. Now, decrease means it refers to some ordering. One of them is smaller than the other one. And how do you say one set is smaller than the other one? Well, if it is included in it. So, aka for any n, I sub n includes as a subset I sub n plus 1. Then, well, you take the intersection of them, and indeed that intersection is in a sense their limit. In many senses it's their limit. Then, so you look at the limit. In other words, the intersection of all of these. Well, this guy says, the theorem says that this set is non-empty. Let me also add perhaps a second part. If in addition their diameters or their lengths go to 0, then in fact this intersection it consists of one point. Let me add it as an exercise. So I look at the length, which means the difference between the endpoints. And if this goes to 0, then there's a unique point in this intersection. There's a unique, let's say, x star, real number, such that the intersection equals x star. Now, without this assumption, that means that I know that this guy, or the conclusion is that this is non-empty, but possibly it has multiple points. But sometimes you want a unique point in the intersection. So how do you prove it? Well, we need to open up what is given. Oh, let me also mention this closed and bounded really stands for some other property called compact. Okay, we're not going to spend time on this, but if you take the sequel class, you're going to spend a lot of time on trying to understand what it means for a subset of an arbitrary metric space or Euclidean space to be compact. But for now, let's just leave it like this. I'm just going to add it as a note here. So that you have some exposure. It's a compact interval. Okay, so how to prove? Well, I know that I sub n is given as a closed and bounded interval. Okay, so let me give names to the left endpoint and the right endpoint. Lambda n for left, rho of n or sub n for right. Okay, and so I should really think of them like this, right? So lambda sub n is a real number. It's an actual number. Rho of n could be actually equal to lambda n. It doesn't matter. But rho of n, rho sub n is it's a finite number also. Now, I know that I sub n includes I sub n plus 1. Well, I mean, drawing the picture, it says that it's like this. This guy is I sub n, and I sub n plus 1 is in there. So let's say this is I sub n, and then this guy is I sub n plus 1. Now, I drew this picture, but you have to be careful when you're drawing things, okay? Now, just because I drew it like this, it doesn't mean that rho sub n plus 1 is strictly less than rho sub n. Maybe this blue interval, the smaller interval, is flushed this way. Okay, all I know that it's in there somewhere. But in any event, that's going to be sufficient because, well, looking at the left endpoints, lambda n is a non-decreasing sequence. And likewise, looking at the right endpoints, rho sub n is a non-increasing sequence. Row 3, row 2, row 1. And in particular, any lambda is bounded from above by any row and vice versa. Which means that lambda bullet is a sequence of real numbers that is bounded from above that increases, and rho bullet is a sequence of real numbers that is bounded from below that decreases. By the monotone convergence theorem, both of these converge. MCT. This limit is the upper bound. So I guess we started at 1. And likewise, okay, and both of these are finite numbers. Okay. Now, the final part I'm going to leave to you, namely that the closed interval from here to there, it could be a point, but maybe it's a closed interval, is equal to this intersection actually. In particular, it is nonempty. Yeah. Inf rho n. Okay, then you're done. So how are you going to show this? You're going to realize you're going to have to argue that any point in this interval is included in any interval, I sub n, and vice versa. If you have a point that is in the intersection of all of these, it must be included in this interval. Okay. Questions about this? Now the next theorem is rather sophisticated, let's say. And I think it's our first theorem with people's names attached. And this is the so-called Bolzano-Weierstrass Theorem. Now we're going to start using subsequences. Bolzano-Weierstrass says that any bounded sequence of real numbers has a convergent subsequence. Now that means that we're going to take a bounded sequence, and somehow we're going to have to sample the frames to get a convergent sequence out of it. Be a sequence. Recall that this was my abbreviation for x bullet being a sequence taking real values. If x bullet is bounded, so maybe I can write it like this: if there's a real number such that for any n, x sub n in absolute value is bounded by capital M. This is what it means for x bullet to be bounded. Then there is a subsequence x prime bullet of x bullet that converges. Oh, R. Okay, so here's the argument. In a sense, it's a nice argument, but and it's almost like an algorithm. It looks like an algorithm, but really, you cannot really sort of take this algorithm and run it on a computer, okay? Because somehow we're going to have to do some sort of binary search to figure out this convergent subsequence. But to figure out, to do the search, we're going to have to go to the end of the tree using computer science language. So let's look at this. Maybe I should give you the idea. Idea of proof. This is one proof. Maybe tomorrow we can discuss yet another proof. But here's what I want to do, okay? I have minus m plus m. That's an interval. I know that all x sub n's are in this interval. It's not escaping. Well, look at the first place. Where is my sequence at time 1? Let's say that we started at time 1. Well, it's somewhere here. Okay. There's a subset to the left of x1, and there's a subset to the right of x1. Let's call them L1, R1. Now I ask myself the following question. Look at all those times after time 1. Okay, 2, 3, 4, 5, 6, and so on. Either my sequence x bullet hits the left interval infinitely many times, or it hits the right one infinitely many times. So how can I write it? Either the number of n's after 1 such that x sub n is in L1, okay, this is a set of times, is infinity. If not this, then it has to be hitting the right side infinitely many times. Now, it might be the case that my sequence is constant, okay? I'm not looking at where I'm hitting exactly. Maybe I'm hitting at the same point. I'm looking at the times, okay? Once you have this, it could, oh, it's not XOR, of course, it's OR. It could be both. Maybe it is alternating like this. It doesn't matter. All I need is that at least one of these is hit by my sequence infinitely many times. I'm going to choose either the left or the right one according to that. So let's say that running out of time, so I'm just going to fast forward. If 1, so this is option 1, this is option 2. Well, let's say that I define I1 to be L1, else define I1 to be R1. Okay? Let's say that it hits this guy infinitely many times. Now do the same argument. So there is some time, let's say x sub n sub 1 that hits this, and then call this L2 and this R2. Again, by the same reasoning, either my sequence hits this infinitely many times or this. Okay? Choose the one that the sequence hits infinitely many times. By induction, this gives a decreasing sequence of intervals which has a nonempty intersection by the nested interval property. We're going to discuss this tomorrow as well, but this is a very nice proof. Okay? Thank you. I'll see you tomorrow. Okay, let's start. Good morning. So I'm taking attendance today. There's a sheet going around. Please make sure you sign it. Second, I wanted to mention something. So one of your colleagues at the end of last class asked about the first midterm. Now, our first midterm is not this Friday, but next Friday during class. So what's going to happen is that this Friday, there's no new problem set, but you're going to receive an email about sort of what's going to happen next week, what our plan is, and so on. And probably I'm going to prepare some sort of document that is supposed to help you out with preparing for the exam and give you an idea as to what you should expect in the exam. I am sort of figuring out those details right now, but you're going to have sort of something. Either it's going to be a mock midterm, or it's going to be sort of like a template or some guide, something like that. I'm not quite sure. I'm working on it. Ultimately, though, because the exam consists of, well, proving certain things, just saying that, oh, you cannot use this theorem, that theorem, and stuff like that, or this exercise, that exercise, it becomes rather inconvenient, and it limits the types of questions I could possibly ask in the exam. So I'm sort of trying to figure that out. But in the meanwhile, I would say a nice way to prepare for the exam would be to take set problems and try to perturb them to get sort of like the correct versions or more sort of like stronger versions and so on. like we discussed a while ago when we were talking about how to approach statements in this class. Okay, so we're going to have a better idea about the midterm by the end of this week. Any questions? Okay, so how are we all feeling about sequences and stuff, convergence? How lost, or how are you are still following what I'm doing? Kind of, sort of, yeah. So this is unfortunate because sequences, even though in a sense it's very useful in applications and stuff like that, because we're not that familiar with this notion of a sequence and convergence and subsequence and all that stuff, especially when it comes to this proof-based calculus class, this is sort of like a hard thing to understand, and it's going to take a while. So today is going to be sort of the crescendo, the climax of this arc, let's say. And starting from tomorrow, we're going to start talking about continuity, continuous functions and stuff like that, which I hope is going to be a lot more understandable. You're going to be able to use your intuition coming from calculus a lot easier. So we're sort of climbing up, okay? And this is going to be the last day where we do this. And then for a while, continuity and differentiability, it's going to be sort of like a plateau in terms of the complexity. And then when we start talking about integration again, things are going to start getting complicated. So you should think of it like this. Whenever in calculus, they sort of like don't say much about how to prove things, well, when it comes to the proof-based class, those parts become more complicated. Okay. Okay, so now last time we were talking about this Bolzano-Weierstrass Theorem, and now I wrote it using plain English. It just says the following: any sequence of real numbers has a convergent. Oh, that's not correct, of course. Any bounded sequence of real numbers has a convergent subsequence. Okay. You see, you need to be careful about hypotheses. Any bounded sequence of real numbers has a convergent subsequence. Okay. And yesterday I mentioned the idea of one of the proofs. And so this is going to be the third proof. I thought it would be a nice idea to sort of discuss two other proofs as well. Now, proof one, this is actually the standard proof, uses monotone subsequence lemma, which I'm going to leave as an exercise, which is over here, plus monotone convergence theorem. Okay? Monotone subsequence lemma says that any sequence of real numbers has one non-decreasing subsequence and one non-increasing subsequence. Maybe these two sequences are the same. Constant subsequences are both of them, of course. So here's an idea as to how to do this. Well, you sort of do a decision tree. You look at the tail set. So for any n, let's define the nth tail to be, well, all the terms of the sequence after time n. So x sub m, where m varies in integers starting from n. So that's the running tail. As I increase n, this tail keeps running to the end of the sequence. Now what you're going to do is this. You're going to say either for each n, t sub n has a minimum, or not. Okay. Exists. So it's the least element in Tn, or for some time n, let's call it n star, min of the n starth tail does not exist, which is the negation of this statement. And then based on either this assumption or this assumption, you're going to create this subsequence. Instead of looking at mins, if you were to look at maxes, you would get the other one. Okay, so this one Okay, so if you look at mins, I think it generates the y bullet, the non-decreasing sequence. And if you look at maxes, it generates the other one. Maybe it's the other way around. It's a very nice exercise. Okay, so this is the first proof. Monotone subsequence lemma, together with monotone convergence theorem, implies the Bolzano-Weierstrass. Oh, there's an attendance sheet. Did we all sign it? Okay. Let me count it as well. 3, 6, 7, 8, 9, 12, 13. So let's just say this. If I have a bounded sequence of real numbers applying the monotone subsequence lemma, I know that it has a monotone subsequence. But then monotone convergence theorem says that any monotone and bounded sequence is convergent. So that's proof 1. Proof 2 is the proof that Taylor gives in the textbook. It's basically the same idea that I mentioned yesterday, except that instead of using the terms of the sequence that you have, you start with this minus m plus m interval, and at each step you halve it by, you sort of cut it in half. And then you look at, oh, is the left-hand side hit infinitely many times or the right side? Okay? Basically the same proof as the third one, but it's slightly different. So here's the proof that I gave the idea of yesterday. So because my sequence is bounded, I know that there is some m number such that for any n, well, x sub n is bounded from below by minus m and from above by plus m. This is the same thing as saying that absolute value of x sub n is bounded from above by m, of course. Okay. Now I look at, so what was the picture? X sub 1. And call the left side L1. And the right side R1. Then you ask yourself the following question. Well, you realize the following thing. Either you say, my sequence hits this left side infinitely many times, or it hits the right side infinitely many times. So, and depending on that, you sort of like choose yet another smaller interval. So let's call it like this. I sub 1, I'm going to define as L sub 1 if the number of n's after this term that I had chosen, so after 1, such that, well, x sub n is in L1, this. So if I'm hitting the left interval infinitely many times after this first term that I had chosen, I choose as my next interval as L1. Well, if this doesn't happen, then it must be the case the other thing happens. So okay, so now if you want, this defines a certain function whose inputs and outputs are intervals. But this is well defined. Okay. Is this step clear? That this, yes?
Wouldn't you have an equals infinity or change the R1 to be L1 in that second statement?
Say again?
So you say that the number of sets in R1 is less than infinity for the bottom statement.
Oh, thank you. Should be like this. Okay, now it's correct. Yes. Any issues with this? This is a very sort of important step in the proof. This is a well-defined way of defining the next step of the intervals. Yes.
Can you explain what you mean by hitting it infinitely?
I'm looking at this set. This is a set of times. Okay? It's a set of positive integers. Because after all, my sequence could be a constant sequence. But the time, I have infinitely many. Okay? So I'm looking at the times after time 1 such that my sequence is in L1. I was using this more evocative language. But this is like x sub n. So at time n, the sequence hits L1 is what I'm saying. And I'm saying the number of such times is infinity. Yeah. The point is that either this, but if this doesn't happen, then the other one has to happen. Because I have infinitely many times, after all. Okay? And like I said yesterday, from a sort of computer science perspective, even though this is sort of like looking like an algorithm, you wouldn't be able to run this because you need to see the end of time. You need to see, oh, am I hitting this guy infinitely many times or the other one infinitely many times? But then again, of course, from a computer science perspective, there is no sort of sequence that is defined for all time also. So I'm sure there are quantitative versions of this also. But in any event, so this is what you do. And then what you say, so let's say that it's this one. Well, let me not call it anything. The point here is the following, okay? So maybe I should be more clear here as well. So to define the subsequence, I need a j function that is strictly increasing. So I'm defining j of 1 to be 1. In other words, this term is also going to be the first term of my subsequence. But for the second term of my subsequence, what I do is the following. Because maybe, let's say I1 turns out to be L1 based on this description. This doesn't say anything about, oh, the fact or the possibility that maybe from time 2 to 10 billion, my sequence hits this one. So I need to keep skipping. I'm going to skip times until I hit this. Okay? There's a time after 1 that hits this, and there are infinitely many. I chose it. I chose I1 according to that. So there is an N1 after this, after time 1, such that x sub N1 is in I1. Okay? So now this number is going to be j of 2. Okay? J of, maybe I should have called this n sub 2 actually, to not confuse it too much. Okay, yes. And then I keep iterating the same idea. Namely, that now I have this interval, I1, and inside it somewhere I have x sub n2. Now I'm going to call, so L2 is, well, I can write it like this, right? So I can say this is the subinterval of I1 consisting of all terms, all numbers to the left of this second term that I chose, and then R2 is going to be the complement. In other words, this is going to be the set of all those numbers that are greater than or equal to this term that I chose. So the idea is that now this is L2, R2. Okay. Now what is the next step? Now I need to define an I2, and I'm going to define I2 or I sub 2, depending on whether or not my sequence hits this infinitely many times or that infinitely many times. Okay. So but now, instead of looking at times after 1, I'm going to look at times after n sub 2. Okay? Yes.
Do you not also look at times after n equals 1 because...
Well, yes, in particular. That is true, of course. But the thing is, I don't want to go back when I'm creating my subsequence. I want my time to proceed, okay? Yes?
Would this be considered a proof by induction?
Exactly. Yes, I'm setting up the induction. Now, if you want to be proper, you should be like, if I chose the nth interval, and then here's how I choose the n plus first interval. But in practice, typically people don't write it that way. Typically you just like tell how to choose the first one, and then the second one, and then you say, by induction, that's how you do this, okay? It's clear how you're supposed to be continuing, which I'm going to say actually here. By induction, I bullet is a decreasing sequence of closed and bounded intervals. Okay. Now, at this stage, I can use the nested interval property, which, in fact, is what Taylor uses also. I can do a bunch of things. But here's what I can do. I can say to myself, oh, in my sequence, I bullet. Either I chose some left interval infinitely many times, or some right interval infinitely many times. Okay? Based on that choice, I have either a non-decreasing sequence, non-increasing sequence, or a non-increasing sequence. So let me do this. So either the number of n's such that I sub n equals L sub n is infinity. It's not an XOR, but it's an OR. Infinity. Could be both. Maybe I keep taking the left one and then the right one inside the left one and then the left one inside the right one, which was inside the left one, and so on. In any event, if this is the case, then looking at the left endpoints of those ends that correspond to the left intervals gives me a non-increasing subsequence. Of INs gives a non-increasing subsequence. If this is the case, well, the right endpoints of those times for which In equals Rn gives me a non-decreasing subsequence. Gives a non-decreasing subsequence but these are in any case bounded because the original sequence is bounded by the monotone convergence theorem. This converges or this converges, depending on the situation. And that's the end of the proof. It's a heavy proof. Pretty much all proofs of it is rather complicated. And certainly in the exam, I'm not going to ask you to prove it. This is something that we're going to keep using, though. Okay? At the very least, you should be comfortable with the statement. Whenever you have a bounded sequence, you can sample out a subsequence that converges. Okay. So if you're confused about this proof, this is probably the most complicated proof that we did so far. So it's okay. It's okay to be confused about it a little bit. But any questions? And I'm happy to discuss this even further. Oh, I should also say something. If you want to really understand certain proofs, a good idea is to take a specific sequence and run the algorithm, or pseudocode, let's say, that is implied by the proof. Okay? You take your specific sequence, maybe let's say, well, here's an example that we did. We showed in class that this converges to 0, of course. That was an example. I'll take this and run this, the pseudocode that is underneath this proof. Okay? So if you want, you can sort of like jazz it up a little bit. You can say something like this, right? So you want to take, let's say, well, x sub n equals 1 over n if 2 divides n or 1 otherwise. So now I've spliced two different behaviors. I've put together one constant signal and one decaying signal. Okay? Take this, run through the proof. What are these sets? What are these intervals and blah, 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 to make it concrete. Okay? So ultimately, this algorithm, this proof, should detect either this subsequence or this subsequence eventually. So the sequence that decays to 0 or the sequence that is constant. Okay. Okay. So okay, let's do this. There's so many important things, but I just want to move forward with different topics. Okay, let's do this. Now, there is a sort of different property that the sequence of real numbers, or a sequence in an arbitrary metric space, can have, which is very useful, and it is the property of being Cauchy. Okay? So I'm going to leave it, I'm going to write it just as a claim. I'm going to take a metric space, so I have a set together with a notion of distance. And let's let X bullet a sequence. Okay? Then I'm going to write down the statement and then say a couple words about what I mean. The sequence is convergent implies that this sequence is, this is a new term, Cauchy. This is the name of a French guy who was into these things. I'm going to give you the definition in a second, which then implies that it is bounded. if in addition you know that this space X is actually the reals, and the metric is the Euclidean metric that we discussed, then in fact any Cauchy sequence is also convergent. So this is upgraded to an equivalence. Addition. Convergent if and only if Cauchy. Now, what is the definition of a sequence being Cauchy? Well, it's something that is implied by convergence. The idea is the following. The notion of a convergent sequence is an absolute notion in a sense, in that you have a target limit, and you're asking if you can approximate that target limit arbitrarily closely using terms from the sequence. Well, maybe you don't know that target, okay? And maybe all you know is that if you wait some finite time, your sequence stops being volatile, meaning it doesn't move too much. And that's the notion of Cauchiness. Instead of having sort of like an absolute notion, you have a relative notion of not moving too much. And so let me write this down. This definition, so the definition of X bullet being Cauchy, for any epsilon, there is an n time such that for any 2 times after n, the distance between the nth and the mth terms is bounded by epsilon. Okay, so the idea is that if I were to wait long enough, this says that my sequence doesn't move too much. It still might move just a little bit, but it doesn't move too much. And how can I define X bullet being bounded? Well, what I can say is that X bullet is bounded if the diameter of its image is finite, where the diameter of a subset of a metric space is defined like this. You take the distance function and then you optimize it. You take the supremum of this, where the inputs are varied in the set. Okay, that's the diameter. Now the point here is that in the abstract setting, convergence implies non-volatility, asymptotically speaking, but not vice versa. Just because a sequence asymptotically stops being volatile, you cannot just say it converges to this absolute limit. But the beauty of using the real numbers is that in the real case, it is indeed true. These two are equivalent. Okay? Now, do I want to prove this? I do want to prove it, but I want to speak about limsup and liminf. These are more useful terms in a sense. Let's just leave this as a theorem for now. Maybe we'll prove it later, okay? Proof later, possibly, maybe. Of course, it's in the textbook, and you're welcome to try to prove it. It's not very complicated compared to the proof of Bolzano-Weierstrass, but still. Let me also give it as a definition. A matrix space is called complete if any Cauchy sequence converges. It's a very important definition. If Cauchy implies complete. In other words, this part of the theorem says that the real line, together with the Euclidean distance, is a complete metric space. And to sort of distinguish these two notions of completeness, completeness that we were discussing before, that we took as an axiom, that's really called Dedekind completeness, and this is called Cauchy completeness. And this is sort of the more general notion that is more applicable. Okay, so if you have time, maybe today, maybe some other time, we can prove this. It's a wonderful proof, but I'd rather speak about limsup and liminf. These are very important. And really, while this is a foundational and technical result, the notions of limsup and liminf, once you understand them, are going to bump up your math literacy. That's why I want to spend more time on this. You can say lower limit, upper limit, and so on as well. Now here's the idea. Oh, these are, let's just say these are specific for sequences of real numbers. Okay? So you have some measurements, let's say, starting from time 0. And you have a bunch of real numbers, okay? Now, yesterday we talked about how the limit of the sequence is really something like the summary of this data. So you want the limit. So this is supposed to be a summary. Asymptotic summary, if you want. Well, but what if the limit doesn't exist? What do you do then? What you do is, well, you get the best upper bound for the limit and the best lower bound for the limit. Okay? So the limsup of the sequence that I haven't defined yet, but I'm telling you what they are, how they operate, is the best upper bound, so the least upper bound, for all possible notions, all possible limit values. So is the best least upper bound for candidate limits, let's say, and liminf is similarly the best lower bound, so the greatest lower bound for candidate limits. Is the greatest lower bound for candidate limits. I still haven't defined these things, but before defining them, let me give you a very nice example, okay? In the textbook, there's a very similar example, but I think this example is better because I came up with it. So let's look at this. Minus 1 to the n times 1 plus 1 over n in parentheses. At time n, I want it to be minus 1 to the n, 1 plus 1 over n. Okay. Now this is a sequence, okay? It doesn't have a limit, doesn't converge. And when you think about it, what is happening here? As I keep increasing the time parameter, this part keeps oscillating between plus 1 and minus 1, whereas this part converges to 1. So in a sense, as time goes by, this sequence keeps oscillating, but it oscillates less and less. Okay? In a sense, you would say that this 1 over n over here is transient. Asymptotically, this shouldn't matter too much. This is going to stay, this is not going to stay. And if I were to plot this, or if I were to look at some values, let's say x sub 1 is what? So this is minus 2. X sub 2 is, well, 1 plus 1 over 2. X sub 3 is minus 1 plus 1 over 3. And then x sub 4 is 1 plus 1 over 4, and so on. So if I wanted to plot this, perhaps I would plot it like this. So let's say this is 1, this is minus 1. And then here is 2. In a sense, because this part is transient, asymptotically this should decay. Ultimately, plus 1 and minus 1 should be sort of like the asymptotes for the sequence. The sequence doesn't converge, okay? Still, I can say something about what it's doing, and I can try to summarize it still. And at time 1, let's say we started here, and then, minus 2, of course, sorry. So, starting here, minus 2. Time 1. Time 2 is 1 plus something. So it's maybe somewhere here. Okay? So maybe I should draw some candles. Okay? And then at time 3, it's going to be near minus 1. So it's going to be like this, somewhere here. And then at time 4, it's going to be here, and so on. So ultimately, there are these kind of cones, or I don't know what to call them. Envelopes, if you want. Okay? So the blue part corresponds to this part. And the red part corresponds to this part. The limit doesn't exist, but the limsup of this is going to be the best upper bound. And so the best upper bound for the limit is going to be 1, and the best lower bound is going to be minus 1. Okay. So what is the alternative? The alternative is to look at the trail of this, and in which case you would see something like this. So I have here one point, and then here another point, and then I have a bunch of points. Okay, so this is the trail. If I don't want to look at the supremum of the trail, okay, supremum of the image, because the supremum of the image also takes into account the transient behavior that I'm not going to see asymptotically. Okay, so somehow what I need to do is I need to keep pushing this trail. I don't want to look at every single value that I hit for all time. I want to get rid of the values that are going to decay, asymptotically speaking. Okay, so does this make sense? This is the intuition behind limsup and liminf. The definitions are going to be rather scary, perhaps. Limit does not exist. Limsup is going to be 1. Liminf is going to be -1. Okay, here's the definition for limsup and liminf. I'm going to look at the tail sequence, or the tail trails or tails, and I'm going to keep I'm going to do a minimax over it. Limsup, as n goes to infinity of x sub n, is literally going to be the limit of the suprema. In other words, this is going to be inf over n sup over m, where m is bounded from below by n of x sub n. This always exists. Maybe it's minus infinity, maybe it is positive infinity. I don't care what the sequence is, this always exists. Okay? Liminf is the other way around. Sup inf x sub n. Again, this always exists. These are the definitions. Okay. So you see, for fixed n, I look at the trail. I look at the upper bound, or best upper bound for the trail, and then I let the tail go to infinity. Okay. That's literally the idea. Let me perhaps write it like this as well. This is also the limit as n goes to infinity of the sequence consisting of the sups. And likewise here. This should be m. It takes a while to understand this. These are very useful concepts, okay? Because they always exist. You're going to have some measurements. You want to summarize it. You want to take the limit. Well, typically the limit doesn't exist, okay? But these guys always exist. Furthermore, if they are the same number, that is equivalent to saying that the sequence converges. So this captures the best upper bound, and this captures the best lower bound for possible limits. And then if they are the same, that means that there's exactly one possible limit. Okay? I'm going to leave this as an exercise. It's a very nice exercise. I highly recommend that you spend a lot of time writing the proofs carefully. And once you understand this, you're going to be able to read a lot of math, let's say, and sciences and stuff. These two notions are pretty much the most useful notions coming from this class, I would say, single variable calculus in sort of general sciences. So, if I have a sequence of numbers, first of all, limsup and liminf, in fact, are limits of certain subsequences. Of some subsequences. Of x bullet. Second, any subsequential limit, so limit of some subsequence of x bullet, is in between these two. If x prime bullet is a subsequence, and x prime bullet, let's say, converges to x prime infinity, then liminf is a lower bound for this limit, and limsup is an upper bound. Third, the original sequence itself converges if and only if limsup and liminf are the same number. That's a finite number. So in which case this number is the limit. Okay. I know that's a lot, but I just wanted to mention a little bit. As time goes by, we're going to keep using these notions. I sort of fast forwarded these a little bit because the first time you see these, it doesn't make too much sense. And then once you start seeing them in sort of certain contexts, it starts to make more sense. And so let me also say one word about this. The limit of a subsequence is a candidate limit in a sense, okay? And so limsup and liminf bound candidate limits. When I said that, I meant the second part. And these are all, I think, proved in the textbook as well. And you're more than welcome to have a look. Okay. We have a couple minutes. So this is all I wanted to say about sequences and subsequences. For a very long time, we're not going to deal specifically with sequences and subsequences, but in problem set 4, you're going to see probably a bunch of problems about limsup and liminf. And then starting from tomorrow, we're going to talk about continuity. And I hope for a while, things are going to be smooth sailing, of course. Okay. So that's it. Thank you. I'll see you tomorrow. Okay, let's start. Good morning. Taking attendance today. Here's a sheet. Please make sure you sign it. So we're done. We're done with talking about sequences, at least for a while. But we're not done with sequences themselves. Instead of just thinking of sequences as things that record data, we're going to start using sequences for more foundational purposes. So somehow now throughout this class, we're going to have a bunch of properties and definitions and all that stuff. And sequences, convergent sequences or some other types of sequences are going to be one of the main tools with which we can probe certain objects and determine certain properties. So let's start with the definition. I'm going to give the more general definition that is applicable for metric spaces. So let me let x and y be two metric spaces. Okay, so x is a set, and on it there's this function that we defined called the metric. You feed to it any 2 points on x or in x, and it gives you as an output some non-negative number that is supposed to say what is the distance between these 2 points that you fed to it. And it has to satisfy certain axioms that we discussed, but I'm not going to remind you of those. And I have yet another set, y, with yet another metric on it, d sub y. Let me let a function f from x to y And well, let me take a base point. So let's say x star in x. I'm going to call f continuous at, I'm going to say that f is continuous at x star if the following thing happens. So you see, the notion of continuity is a local notion. If, well, you need a logical statement. Let me write down the statement, and then we can discuss what it would mean, or how you should think about it. For any epsilon positive, there is some delta. This is the infamous or famous epsilon-delta definition. Again, positive, such that for any x in x, if x is delta close to my specified point, x star, then the images I want to be epsilon close. So if x is delta close to x star relative to the metric specified on x, then I want this to imply that the images relative to this other metric that is defined on the image or the target, I want their images to be epsilon close. Okay, that's the definition. Okay. Now, what is going on here? The idea is this. Okay. Now, remember this n epsilon of room principle. Let's say that you have an archer. Okay. Well, I guess it should be like this, perhaps. This. And you have a target. Okay. I'm just trying to justify why this order of sort of variables. So f is your arrow, okay? Or rather, it's the archer itself. Your x is going to be your different options for how you're going to throw your arrow. Maybe you're going to throw it fast, maybe slow. It depends on where you're aiming at, blah, blah, blah. But in any event, you have a target here, the center, which is f of x star. You want to approximate that. Now, you say the following then. Okay, I could be Robin Hood or blah, 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 but if I'm a normal person, instead of just trying to hit the bullseye, let me just make sure that I'm hitting the target somewhere, at least maybe here. Okay. So you start with a simple, rather easier, let's say, objective. Instead of hitting the bullseye, let me just at first hit the target itself. I don't care where I hit it. Okay. Now, based on that, no, thank you. Did we all sign this? Based on this rather relatively easy aim, relatively easy goal, you say, oh, okay, like I need to train a little bit and so on, but I'm sure I'll be able to do it. Now, based on that, what this is saying is that you chose your epsilon to be large initially. You're not trying to be too accurate. And then based on that, you need to have some accuracy. Obviously, you cannot throw the arrow that way and aim to hit it. But still, you have some delta. Okay? And then insofar as you're aiming, according to this delta, you're going to hit the target. Okay? Then you say, okay, now I can consistently hit this target. Let me now try to hit it more accurately. Now I want to hit specifically somewhere here. If I can hit even closer, that's fine, but I don't care about that now. I'm trying to upper bound the error margin. Okay? So now you shrunk epsilon just a little bit. That's going to require more control. So delta is going to shrink a little bit also. But insofar as for this shrunk delta, you have some control on the arrow that is within this delta, you want to make sure that again you're hitting this smaller disk. And you keep going like this. Okay, you take epsilon smaller and smaller. The point being is that first you take the error. Based on that error, you decide how much control you need. Okay, this is the intuition, no matter how abstract a notion of continuity you have. And once you understand this, it's going to take you far. Okay. Any questions about this? Continuity is one of the important concepts, of course, of calculus, and that's why I'm sort of slowing down a little bit. Yes?
What does the metric being less than delta mean?
It's not the metric. It's the distance between these two. Read it like that. The distance between x and x star relative to something. Right? I might have different metrics. That's the point. Okay, right? So it's like you're trying to optimize something. But optimization is always relative to a certain metric. Okay? Cost function, if you want. Yeah. If you're doing machine learning, for instance, a metric, an example of a metric is a cost function. They're not exactly the same thing, but they're very related ideas. Any other questions? All right, so once I feed this x and x star into D, this is now a number. It's a literal number. And I'm saying this number should be less than this number. I chose delta to be a number also. Okay. Yes?
Is there any relation between delta and epsilon? Like, can we say that delta is less than epsilon?
That's a very good question. So if you want to be more quantitative, you actually want to say delta is a certain function of epsilon, and you want to have delta equals delta of epsilon. Maybe we can talk about this, and this leads to this idea of a modulus of continuity. There are certain properties like Lipschitz, Hölder, blah, blah, blah. I, in fact, mentioned those in the syllabus as optional topics. If you have time, I would like to discuss those as well. But yes, in applications specifically, you don't want to say for any epsilon there is some lofty delta that comes from somewhere. You want to say what the delta is as a function of epsilon. Yeah. For applications or for sort of like more sophisticated issues. Because often you have these estimates and then you have some other things as well, and like you want all of them together. And so you need to be more careful about how you're choosing deltas and all that. But that's a very good question. Yeah. Any other questions? Okay. So I'm going to call f continuous without specifying the base point if it is continuous at every point. Okay. At x for any x star. And let me introduce a notation C0 of x comma y as the set of all continuous functions from x to y. This is one of the important function sets that we're going to use in calculus. C0 xy is the set of all continuous functions from x to y. later on we're going to talk about, not today, but possibly on Friday, what it means for a sequence of functions to converge. But you don't want some arbitrary functions. You want at least continuous functions. And you want the limits to be a function, of course, but you want the limit to be a continuous function also. So we're going to have to understand this set as a metric space in and of itself. And that's where this idea of a uniform metric come into play. For now, let's just take it as a set. And let me also mention y0. Once we start talking about differentiability, we're going to put different numbers there. And so this really tells you how many times you can differentiate and still get a continuous function. So C1 is going to be a differentiable function whose derivative is continuous, and so on. Okay, so we're going to sort of build up. This is sort of like a common notation. And then you can put fractional values here to sort of like specify this epsilon-delta dependencies. Okay. It turns out that there are certain functions that are 1/2 differentiable in a sense, okay, which we might talk about.
Is that like related to fractional calculus?
It could be related to fractional calculus, but it's not as complicated as that. Yes. Yes. Okay. Any other questions? Okay. So now let's connect this to the idea, to the notion of a sequence. How to relate continuity and sequences. Well, a function is continuous at a point x star if and only if it preserves convergent sequences that converge to x star. Okay. Did we all sign the attendance sheet? Okay. So in a sense, continuity for functions is something about preserving summaries of discrete signals. Okay. So let me write that down formally. It's a good, let's call it claim. In the same setting, not going to write down the metrics. It's continuous at x star. If and only if for any sequences, let's say starting at time 0, that converge to x star, well, the image sequence converges to the image. If x bullet converges to x star, then f of x bullet, I want to converge to f of x star. In other words, f has preserved limits, right? So using the limit notation, what I'm saying here is that limit of f of x sub n as n goes to infinity, I want this to be equal to f of the limit. Okay, it's the same thing. In this case, of course, this guy is x star. Okay? So somehow sequences or convergent sequences contained in them this epsilon-delta definition, which is a convenient thing, which I hope you're going to come to terms with eventually, that using sequences, while initially kind of awkward, it's rather convenient because it allows you to argue about things in a sort of discrete time step manner. Okay. So let's prove this. So this is a two-sided statement. So I need to show that if this epsilon delta thing holds, then the second thing holds, and vice versa. Okay. Let's do this direction first. So I'm supposing that this epsilon delta definition holds. That's my definition. Now I need to show this statement. So what do I need to do? I need to take a statement, I need to take a sequence, x bullets in x, that converges to x star. And I need to do something that guarantees that this happens. Okay? Let x bullet be a sequence that converges to x star. I want this. Okay, what does this mean? Well, I can just open up the definition. So this is a sequence in y that converges to this other point in y. Okay, now I need to write it out. AKA, for any epsilon, there's a capital N such that after this capital N, right, the distance between the nth term and the target is bounded by epsilon. This is what I want. Now to verify this, I further take an epsilon, okay? I'm going to take an epsilon. Now I need to find the n. I need a capital N now. Okay? I need a capital N such that after this capital N, this f of x sub n is epsilon close to this guy. See, I'm just unfolding the definitions, and I'm just fixing variables as they come. Okay? So now, at this point, I need to use, well, I have two things to use, right? This guy converges to this, and the continuity of f. Maybe it's good to use colors. Let me use blue for this epsilon. Plugging in the blue epsilon in the definition of f being continuous, I have that there's a delta blah, blah, blah. Okay? For the blue epsilon, so by the continuity of f, so you're trying to sort of chain multiple logical statements together. For that epsilon that I chose, which was arbitrary but fixed, there is a delta such that blah, blah, blah. There's a delta such that for any x in x, I know that if the distance between x and x star is bounded by delta, then the distance between their images is bounded by this blue epsilon. Okay, so I use the continuity of f. that's the final thing I can use over here. Because x bullet converges to x star, in the definition of this sequence converging to this, we always started with for any epsilon blah blah blah. But now, this is the thing that sort of bounds this distance. So I want to use as epsilon in the definition of x bullet converging to x star delta. Okay? So maybe I should use red here. Since for the red delta, there is some capital N such that after it, the nth term of my sequence will be red delta close to the targets. Okay. But then if for all lowercase n after capital N, this happens, by chaining this with this, I also have that the images are epsilon close. So putting these two together implies that for any n after capital N, d of f of x sub n, comma, f of x star is epsilon close, epsilon being the blue epsilon. Which is what I wanted. I want today to be a slow class, but I don't want to rush these things too much. And since I haven't done too many proofs about these types of epsilon delta management, I think it's good. And ultimately, when you're doing proofs, of course, you don't need to write things this explicitly. Right, so ultimately, I was able to say that for any epsilon, this blue epsilon, even though I fixed it, it's arbitrary. I didn't use anything specific about the blueness of the epsilon, for instance. Right? For any epsilon, I was able to find a capital N. This claimed capital N is this N over here that I found. And then I realized, by doing some logical chains, that after this capital N, indeed, what I wanted is true. Okay. Any questions about this? When you're first learning these things, and when someone else is doing them, it looks obvious, but then you try to do it yourself, and then it gets more complicated somehow. Okay. So, questions about this? This is one side. How about the other side? We assume continuity. We show that continuous functions preserve limits. Now I want to do it the other way around. And instead of saying, let's suppose that f is like this, and then showing the epsilon delta, let me go the contrapositive direction. Okay? Now I'm going to assume that f is not continuous. And then I'm going to find a sequence whose image doesn't converge. Okay? Proof of the other side. Instead of proving this implies this, I'm going to prove not this implies not this. So say f is not continuous at x star. opening up the definition, now I need to negate everything. Right, maybe let's do it again. So for any epsilon, first write the positive statement and then put a negation in front of it. For any epsilon, there's a delta, such that for any x in x, if the distance between x and x star is bounded by delta, then the distance between f of x and f of x star is bounded by epsilon. Now I need to negate this. What was the rule? You keep the order. For alls turn into there exists turn into for alls. Okay. Now this is the good thing about logical using logical symbols, because it's basically algebraic. You don't need to think too much about how to negate things and so on. So there exists an epsilon. Let me use epsilon 0. It's a specific one. For any delta, there's an x such that now I need to negate this statement. If this, then that. How do you negate it? You say this, but not that. But, so x is x star, so x is delta close to x star, but their images are not epsilon close. That is to say, they are far. But d of f of x and f of x star is bounded from below this time. You see, I'm negating it. Now this is what I have. So this statement, negation, is logically equivalent to this. I'm not going to change epsilon 0 here. What I have control over, what I can change, is delta. For any delta, there's an x. Okay? For delta equals 1. So what do I need to do? I need to come up with a sequence that converges, except its image doesn't converge. So now that you have a logical statement like this, you can farm it to construct a sequence, okay? And the only thing you can move here is this, initially speaking. So let's do this. Delta equals 1. For delta equals 1, I have some x, okay? Let's call it x1, and so on. Let me do it here. Maybe again, let's use colors. It says for any delta, positive number. In particular, I can choose whatever number I want, okay? The moment I choose a delta, I'm going to have an a point. There is and let's use another color here. Let's use blue. There is an x. But instead of saying just x, because this specific x depends on delta being 1, I'm going to call it x sub 1, okay? In x, such that x1 is delta close to x star, but its image is farther than epsilon star compared to f of x star, such that d of this, it's blue. If you're trying to understand statements like this, I would highly recommend that you take your time, write everything explicitly. Don't rush it. Okay? Be the Bob Ross of epsilons and deltas. but this. Should be f of x1. Now I keep going. For red delta equals, well, 1/2. Okay, I can keep shrinking it. Now, again, I have a new point. Maybe it's the same as before, okay? But I'm just going to index it differently. I could call the same thing different names, after all. There's nothing stopping me from doing that. So maybe I should be more explicit here. So in this statement, delta was 1. Here, now it is 1/2. Okay? And in general, of course, for delta, for instance, 1/n, there is an x sub n such that the same thing happens, but I have the bound 1/n here. Okay, x sub n, x sub n, sub n. Any questions about this? Okay. Now, by the principle of mathematical induction, whatever, you have a sequence x bullets. Okay. PMI, x bullet is a well-defined sequence in X. So maybe I should use blue there. Is well-defined. And it converges to X star, right, by squeeze theorem or whatever. Maybe I should leave it to you as an exercise that x bullet here, the way I constructed it, converges to X star. Okay. Because I have this bound. The nth term is at most 1/n away from the target. I constructed my sequence so that this happens, of course. But on the other hand, if I were to look at the image sequence, f of x1, f of x2, and so on, it cannot converge to f of x star because all of them are farther than epsilon 0 away. Does not converge to f of x star. I assumed not this, I showed not this. For some sequence that converges, the image sequence doesn't converge. Any questions about this?
Should it be like obvious that contrapositive is the way you would
No,
the left side of that?
no.
Would that be something you'd have to do?
You don't have to prove it using contrapositive. When I looked at this, that was what came to my mind immediately. Yeah. And what's going to happen is that as you keep sort of working on these things, typically given a statement, one way of like logical sort of argumentation is going to be more obvious to you, and that's probably what you should go for. Yeah. You don't have to use contrapositive for this. But I know that if I don't assume this guy is not continuous, I can just farm the statement to construct a sequence. Okay? It seems more daunting to me to say, use this statement. It's like, if I have all sequences that converge to this and the image is convergent, how do I get the epsilon-delta? It seems more non-obvious to me. Obviously, logically speaking, they're the same. But see, psychologically, they're not the same, perhaps. Yeah. Here's another question, or maybe comment. Here I used, as these upper bounds, 1 over n. Okay? In fact, here I could have used any sequence that I know decays to 0. If I wanted, I could have used 1 over 2 to the n, so exponential decay. In this case, it doesn't matter. There are other situations where you really need to worry about how you're constructing this sequence. Maybe 1 over n is not fast enough of a decay. Okay? Because, for instance, if you were to add 1 over n's from n from 1 to infinity, that series diverges, right? But 1 over 2 to the n, when you add it up, doesn't diverge. So sometimes you need to add sort of all of these errors together to sort of put it in some other statement and so on. Any other questions? Okay, let's look at composition of functions. The main idea is that the composition of continuous functions should be continuous. Okay? Oh, maybe even before that, let's look at some examples as to how we can apply this. So for instance, this immediately gives that any polynomial function is continuous. Oh, immediately meaning with some limit laws or something like that. So example. I'm just going to take a polynomial function from the real to itself. Well, let's take x to some polynomial. So x sent to k from 0 to n, a sub k, x to the k. That's a polynomial. A sub k is, let's say, fixed real numbers. Doesn't matter. This function is continuous. F belongs to C0. Well, why is that? You can use the epsilon-delta stuff, but you see, because I didn't specify the coefficients of the polynomial, you can do it. It's not impossible, but it's going to be rather cumbersome to handle the epsilons and deltas. But if you use this sequential characterization of continuity, it's rather straightforward. So what do I need to do? I need to take a target and a sequence. By one of the problems in, I think, problem set 3, this problem about limit laws, you know that, for instance, if this guy converges, well, I can multiply it by itself, right? And then that would give me that x bullet squared converges to x star squared, and so on. But then for any constant multiple of a convergent sequence, that multiple is also convergent. a sub k, x to the k bullet converges to x star to the k. But then sums of convergent sequences is convergent. So if I were to add these up, I would get that f of x star converges to f of x star. So in problem set 3, there's this problem about limit laws. Once you do that, limit laws, you hide away all epsilons and deltas and blah, blah, blah into the sequential thing. Okay, it carries everything. And it becomes, so you sort of invest initially into the sequence business, and then you can sort of reap the benefits. Any questions about this? Compared to this, try using the, I don't know, calculus definition or blah, blah, blah. Of course, in calculus, they just tell you that polynomials are continuous. And there are perhaps even better ways of doing this. For instance, polynomials are differentiable, which we're going to see later. But differentiable functions are continuous, which we're going to see also. That's yet another way of seeing this, for instance. Okay. So it turns out that the more advanced math you do, the less math you want to do, actually. Okay? You want to not calculate things. You want to do things in a slick manner. And so again, using these limit laws, I can say that the sum of continuous functions is continuous. Product of continuous functions is continuous. A scalar multiple of a continuous function is continuous, and so on. Maybe let's write those down. Let's say I have two functions that are continuous from x to y. Let's take a constant alpha. Oh, I guess I can take a constant alpha. What do I want to do? I want to take the target to be reals so that I can add things. Yes. And so then their sum also is in the set. Their product is in the set. If g is never 0, f divided by g2 is a continuous function. And of course, a constant multiple of f is also a continuous function. And how to do this? Again, you can use the epsilon delta stuff, but it's going to be rather more painful. What you do is, I'll take a sequence that converges. Let's say, for instance, for this guy. You want to probe the continuity of f plus g. That means that it should preserve the summaries of discrete time signals. Okay? So take a discrete time signal that has a summary. Let's say x star. Well, if this is the case, since f and g are continuous, this means that f of x bullet converges to f of x star, and g of x bullet converges to g of x star. But then these are convergent sequences of real numbers. And by the limit law, you know that their sum converges to the sum of the limits. And of course, that sum is nothing but this. Right? Oop, should be bullets. And this should be x star. See? No epsilons, no deltas, no pain. All about discrete time signals. And the other statements follow the same way from the limit laws. Okay. I think it's a good place to stop. On Friday, we're going to pick up the pace again. Thank you. Okay, let's start. Good morning. Taking attendance again. Okay, so later today you're going to receive an email about the first midterm. So it's pretty much done. I just need to go through it by myself, fine-tune the timing and all that stuff. But generally speaking, the outline, broadly speaking, is done. So you're going to see a template on Canvas. What I did is I took what I have already and I censored the problems themselves. So you see the general shape of the exam. And in the email, I'll also mention how to prepare for it and so on. So most likely, this is what's going to happen. There's going to be 4 problems in it. 4 problems in it. Some of them have parts, but in any event, the first problem is going to be worth, I think, 20 points. Second one is 60, I think. This has parts. Third one is 16 points, and then the fourth problem is 4 points. This also has parts. So this is the harder problem that probably I'm not expecting you to see to have seen problems in this parts in this fourth part, but the other ones you should be fairly comfortable. I took them, most of them, let's say, verbatim from problem sets or some of the exercises that I discussed in class. So if you're comfortable with the definitions of sup, inf, what it means for a sequence to converge and so on, and if you can actually use them in specific examples, for instance, if I were to give you a certain set of real numbers, and if I were to ask you what is the sup of this set, if you can figure that out, and if you can write a formal proof that justifies your claim, then you should be fairly comfortable, okay, with these first parts. And then this last one, again, it's not beyond the realm of possibility, but it is rather more involved, partially because this is going to be something that I didn't mention specifically. You're going to have to sort of get creative a little bit, let's say. Okay, more details later. Any questions about this?
Will all the questions follow proof formats, or should we expect true false?
All of them are true false, but in the context of proofs. So all of them are prove or disprove. They're all like that. Yes. Yeah. Part of the problem is going to be whether or not the statement is correct. So what you might encounter is, oh, it's not sort of verbatim a problem from a problem set, but it's sort of like a corrected version, or maybe it's a false version of the problem that you saw. And so there it's going to come in handy. Now, I should also mention, when it comes to problem sets, I always suggest that you sort of look into how to correct things and so on. But of course, in the exam, your time is limited and so on. So you have to be cutthroat a little bit about it. If it's correct, it's correct. If it's false, there's an example. You write it down. You don't worry about it. Okay? Any other questions? So, yes?
Do you get an index card of notes?
No, nothing. No. In the email that I'm going to send later today, I'm going to mention what you can assume. But okay, yeah. So I like to give hard problem sets, but easy exams, or relatively easy exams. So ultimately, to get a 90 plus in this exam, I don't think it's going to be significantly hard, but to get a 100% is going to be very hard. Okay, that's what I like to do. So these 4 points. So this has 4 parts. Each part is worth 1 point. Okay, so going up to 96%, it's rather doable, but then it's going to get even more harder. So, and this is what happens in general as well, right? So if you want to go from 5 percentile to 4 percentile, it's a lot of work compared to going from 30 percentile to 40 percentile. Okay. And of course, if you're one of those who are going to ultimately go to grad school for math, then you should try to be a completionist about this. But if not, then getting an A in this class is rather reasonable. So that's what you should focus on. Okay, any other questions about this? So continuity, we were talking about continuous functions and so on. Recall that this was my notation for the set of all continuous functions, so C0 from x to y, x and y being metric spaces. Oh, it looks worse. And so here's a fundamental, thank you. Here's a fundamental property. Not too many people today. Maybe they thought that because I took attendance twice this week, I wouldn't take another one. But of course, I'm playing some sort of game theory game underneath all this, trying to maximize. I'm doing math, they take attendance actually. But anyway, so here's a very important property. It's rather straightforward to prove, but very foundational. Namely that if you have two functions, both continuous, of course, insofar as the target of this first one matches with the domain of the second one, I can compose them and get a function from x to z, which we denoted by g o f. Well, the statement is that if both f and g are continuous, then so is the composition. And remember, a while ago we had talked about how we have different foundations for math. We said, oh, we're using set theory for this class, but I mentioned another foundational sort of theory, which is called category theory. And for category theory, instead of taking a set as sort of like the undefinable thing, because that's what I did basically, if you think about it, if you go back to week 1, I just said a set is basically a set. We know what a set is. I wrote definition, but it actually doesn't make any sense. I'm just taking it as an undefined object. In category theory, compositionality is the foundational thing, and then you build everything based on that. But in any event, even though we're not doing category theoretical foundations and stuff, composition is important for us. And so here's the proof, okay? Now I can use the epsilon-delta stuff, right? So I would have one epsilon-delta statement for this guy, and then one epsilon-delta statement for this guy, and then I could try to combine them in some way to get an epsilon-delta statement for this. But in this case, just using this sequential definition of continuity is a lot easier. And recall, what was that? It said that a function is continuous. Let's say f is continuous from x to y if the following, and if and only if the following happens. Any convergent sequence in x under f transforms into a convergent sequence in y. So to verify that g o f is a continuous function, I can take a convergent sequence in x and see if I can generate a convergent sequence in z using g o f. So I take a convergent sequence in x. F is continuous, which means that their images under f is a continuous sequence in y. So f of x bullet converges to f of x infinity in y because f is continuous. Because but then if this is a convergent sequence in y, and if g is continuous, then I can apply g to these to get a convergent sequence in z. And that's the end of the proof. You see these convergent sequences carry with it all this epsilon-delta management. It doesn't always work. Sometimes you need to use epsilon-deltas, but in this case, it's rather pleasant to just do this. Right? You just substitute. It trickles down. Any questions about this? Now, it's a good exercise still to do the same proof using epsilon and deltas, but I'm going to leave that to you as an exercise. Prove the same statement using epsilon and deltas. It's going to help you get more comfortable with epsilon delta management. Okay, so that's good. Here's an example. Yeah, let's look at this. Let me define a function whose inputs vary from 0 to 1, and it takes real values. Let's say it takes an x, sends it to 1 over 1 minus x squared in square root. Now, for things like this statement is rather useful, okay? And the way you use it is not typically like taking the functions and then looking at their composition, but rather realizing that a certain function that is given to you is the composition of functions. So you're factorizing the function given to you. So how can I factorize this? So I can think of it like this, right? So x, let me first send it to 1 minus x squared. That's a nice function. It's a polynomial. Then I'm going to take that, some other variable, I'm calling it. Then I'm going to send it to the square root. Then this I'm going to take it to 1 over z. Okay. Now, so what I'm trying to say here is that f is the composition of these three functions. So maybe I should be more explicit. Let's say this is alpha, this is beta, this is gamma. I'm just saying f equals gamma composed with beta composed with alpha. So to claim that f is continuous, it is sufficient to say that all three of these functions are continuous by induction. Right? So here I have two functions, but of course you can take any finitely many functions by induction. Again, you can keep composing them to get a continuous function. Alpha is continuous because it's a polynomial, like we discussed on Wednesday. So this guy is continuous. Continuity of beta, I'm going to leave to you as an exercise. Beta is a continuous function. And the trick you should use, you may try using, is that you can write x minus y as, well, x in square root squared minus y in square root squared, and then you can factorize this. Using this identity, it's not too painful to show either using epsilon delta or a sequence that beta is continuous. And then finally, this is by one of these limit laws, or by this example that I gave on Wednesday. Because it's the ratio of continuous functions, this is also continuous. And in total, because f is a composition of continuous functions, it too is continuous. That's an example. Of course, you can use epsilon deltas or whatever, but like I said on Wednesday, as you get more and more abstract, you want to do as little math as possible. Okay. Any questions about this? So here's our first theorem about continuous functions. Now I want to specify to functions like this. Okay. I gave the definition in the abstract, but now that we're done with the definition, I want to specialize the context of single variable calculus. The first one is what is called the maximum principle, or you might have heard the name extreme value theorem. How many of you have heard of this extreme value theorem? The idea is that the continuous function should attain its max and min. That's all there is to it. So, theorem. So this is maximum principle or extreme value theorem. Extreme. Now I need to start with a closed and bounded interval. Let I be the closed interval from lambda to rho, so the left side, right side. And I want these to be actual numbers. And let's say that lambda is not equal to rho, so that this is not a point. Let me also let a function f defined on I on the interval, taking real values, it is continuous. Let's split it into two cases, two statements. First of all, item 1 is that f is bounded. So then, f is bounded. And of course, this means that its image is bounded. So it's a bounded subset. Image of f, which is also f of I, is a bounded subset. Of real numbers. And second, f attains its maximum and minimum at certain points in I. So let's say, yeah, I'm going to write it, well, okay. There are multiple ways of writing this. Let's say, what is the nicest way of writing it? Let's write it like this. Max of f exists. So it's not only the sup, but it's the max. And min of f exists. Let's just leave it like this. Well, maybe I should say more, actually. This is a sufficient statement, but when you think about it, saying that the max of f exists, by definition, means that not only does the sup of this set exists, but in fact, that sup is included here. Saying that the sup of this set is included here means that the sup, which is a value, is attained by f of x for some x. Okay? So, note if and only if sup of f is in the image that is to say there is some x in I such that f of x equals the sup which is the max. In different contexts, you could also see, oh, the set of the set argmin or argmax of f are nonempty. So let me write that down as well because that is also very common. So argmax of f, which is the set of all those x's in I such that f of x is the max. And argmin is defined similarly using the min. I want this to be a non-empty set, and I want this to be a non-empty set also. There is some argument that minimizes f. There's some argument that maximizes f. Possibly these two arguments are the same, and possibly there are multiple such arguments. This statement is all about having at least one for these. Okay. Any questions? Yes.
So what do you mean by like argument of max and argument of min?
Well, yeah, so x is an argument for f. So this argmax of f is the set of all those x's that maximizes f. Maximizing arguments. There could be multiple, that's why it's a set.
Cool, thank you. That makes sense.
Yeah. Yeah, the pure math people don't use these very often, but when you switch over to more applied stuff, this is like very common notation. Any other questions?
But that function there, which is continuous and bounded on a subset of the reals,
Yes.
like it does not have a maximum in the real numbers. It approaches infinity as x approaches 1. For nicely behaved functions, I would expect.
Yeah, no, fair enough. But then again, it's not well defined there. So you're right. I should put here like this. Good catch. Yes. Yeah, of course, as your colleague is suggesting, at 1 you have an asymptote here. So very good. It has to be defined everywhere. Okay. Any other questions? Okay. So here's the proof. Let's first start with the first part. Then we're going to use the first part and the second part. What do I need to show? I need to show that f is bounded. In other words, the set of all those y values, so the image is bounded as a subset of the reals. Okay? Say it is not bounded, okay? Say otherwise. Okay, let's be more explicit this time because I think I used this trick before, but I want to be more explicit as to what goes on. So what do I need to do? I need to write down the statement for the set being bounded. So there is an M bound such that for any x, f of x is bounded from above and below by M. Then I'm going to take the negation of this. And what is this equivalent to? This is equivalent to saying that for any M, there is a point x in I such that f of x in absolute value is greater than M. Okay. Any guesses as to how to continue here? What I want to do is I want to take this logical statement and farm it to create a sequence in I. Right? So because it says for any M, I have this. So for M equals 1, there is an x sub 1 such that f of x sub 1 exceeds 1. Right? So then perhaps I can take m equals 2 and so on. You can be a little bit more fancy if you want, and you can say, well, I'm going to take the max of 2 and this guy. Okay? So let's say now I take m to be the max of 2 and this value. Okay? Because x sub 1 is a fixed number in I. This is a fixed number. So I can take its max with 2. Statement gives me that there is an x sub 2 in I such that, well, f of x sub 2 in absolute value exceeds M. And so this was 1 here. Exceeds M. It exceeds 2, but in particular it exceeds f of x sub 1 in absolute value. Okay, and I can keep going like this. Now, ultimately then, I have a sequence x bullet in this closed and bounded interval such that when I apply f to it, this sequence in absolute value is strictly increasing. Okay, it's escaping from the origin. So, by the principle of mathematical induction, x bullet is a well-defined sequence in I, and its image under f with absolute value diverges to infinity. By the monotone convergence theorem, if you want. Okay, it's unbounded, and it is strictly increasing, so it has to go to its soup. Any questions about this so far? So I have a bounded sequence whose image blows up. Okay. Well, if I have a bounded sequence, right, because this is a closed and bounded interval, which means that this is a bounded sequence, Bolzano-Weierstrass tells me that I can sample a subsequence that converges. Okay? There is a subsequence, and there's a number in R such that x prime bullet converges to x prime infinity. Now I'm going to leave it to you as an exercise to realize that, in fact, this limit has to be in I. It cannot be some arbitrary real number. It cannot escape I itself. This is actually what it means for an interval to be closed, but never mind. You're going to see that in the sequel class if you do take that class. Okay. Well, then I have a sequence that converges to something in the domain if it's continuous, which means that its image also has to converge. Continuity of f of x prime bullet has to converge to f of x prime infinity. Okay. Now we're almost done. Namely that this cannot happen because x prime bullet is a subsequence of x bullet, which means that its image is a subsequence of this sequence that diverges. Okay. You cannot have a sequence that converges and diverges at the same time. So we have the second part. I shouldn't forget. So what can we do? Here's what I can say. For instance, I can open up the definition of this sequence converging to that point. So for any epsilon, there is a blah, blah, blah. Let me choose epsilon to be 1. There's an n such that for any n after n, the difference between these two is bounded by 1. Which means that f of x prime bullet is bounded, which is a contradiction with this. So let's say star. Where star is this? In other words, because everything, I'm assuming that everything I said in between is correct, which means that the first thing that you said was wrong, which means that this is false. In other words, it cannot be otherwise, so that it has to be bounded, the image. So that's the end of the first part. Any questions about this? If you want, you can even be more sort of explicit, what is this bound? You can explicitly say. Well, if you want to bound this, after capital N, this is at most f of x prime infinity plus 1. Okay? But then before capital N, I have only finitely many terms, so I can take the max of that as well. So I can say this. Max of, what is it? F of x prime infinity plus 1. And then, well, the max of f of x sub n prime, where n is at most capital N. The point here is that because you're taking the max over a finite set, this is a finite number. Okay. So you're controlling how large this f of x prime sub n can get before this special time n by just taking the max of all of those prior times. And then after that capital N, you know that this is going to be not farther than 1 compared to this guy. So I can bound after this special time this guy by this plus 1. So that gives you an explicit upper bound. Okay. Sometimes you end up needing to have specific upper bounds, explicit upper bounds that work for your thing. Okay, so that's the first part. Second part says that in fact there is a point in I that becomes the max. What do I want? I want an x value such that f of x becomes equal to the sup. Well, let's first note this, okay? Because f is bounded, in other words, image of f is bounded, and because it is nonempty, by the completeness axiom, sup of f is a finite number. So by the completeness axiom, sup of f is a finite number. And furthermore, again, by definition, sup of f is supposed to be an upper bound for any f of x. Okay. Now let's do this. Again, by using this procedure of farming statements, what you can do is you can generate a sequence that strictly increases to sup of f. Let's say there is an x bullet in I, strictly increasing. No. There's a sequence such that the image is strictly increasing. There's an x bullet in I such that f of x bullet is strictly increasing with limit sup. So the image converges, but not necessarily the original sequence X bullet. But again, I can use Bolzano-Weierstrass to sample out a convergent subsequence. Okay. So there's a subsequence, there's a point in I such that X prime bullet converges to X prime infinity, but then continuity of F says that F of X prime bullet converges to F of X prime infinity. And then here's the final step that I'm going to leave to you. If a sequence converges to something, then any of its subsequences too converge to the same thing. Okay? So, exercise. F of X prime bullet is a subsequence of F of X bullet. So they converge to the same limit. In other words, this limit equals this limit. That is to say, sup of F is attained exactly at F of X prime infinity. And that's the end of the second part. Okay. And then finally, to get the statements for the min, what you can do is you can apply the same statement for minus f. For the statement with min, consider minus f, which you know is continuous because it's the scalar product, the scalar multiple of a continuous function. Okay, and that's how you do it. Questions, comments? Is this hard or kind of hard? Yeah. Yeah, especially when you're first sort of learning this stuff, because there are so many definitions underneath that govern sort of like the things. Yeah, I agree. It's not easy. But you know, that's how you learn. Yeah, try to sort of like go through it yourself and stuff. And if there are any confusion, I'm happy to set up office hours or some meetings and so on, so that we can discuss further. And maybe the issue is that I'm not sort of being explicit enough and so on. Part of it is that sometimes when you get more explicit, things become more complicated. So for instance, in this argument, for instance, I have this bound, but I don't know if it helped at all when I said this explicit bound actually works and so on. So analysis is one of those areas in math that you can sort of like do very softly without sort of like being too careful about bounds, or you can be very quantitative about things and just like squeeze all the juice out of whatever you have. Okay. And sometimes you end up needing to sort of squeeze the estimates and so on. Of course, it's not our concern in this class to be super quantitative about things. Getting a qualitative understanding is first. Okay. In applications, of course, you don't need to have specific estimates typically. Any other questions? Now, in this statement, I'm not saying anything about the uniqueness of this argmax or argmin. Okay, because if you have a constant function, well, the minimum of f is the same thing as the maximum of f, and that value is attained at any point. Okay? This just says that there's at least one point where you attain the maximum. Maybe there are multiple points. Okay, so we have a couple minutes. It's too short to start a new theorem, but I think I'm going to state the next theorem that we need to discuss, which is the intermediate value theorem. How many of you have heard of this? Intermediate value. Okay, more. And now the idea is that if you have a continuous function that goes from this height to that other height, let's say, well, it has to attain every single height in between. It cannot jump, basically. Let's say, we're going to discuss this more on Monday. Say in the same context, f of lambda is strictly greater than f of rho. So if you were to draw the graph, here's one point, here's the other point. Okay? This is lambda, this is rho, this is f of lambda, this is f of rho. Intermediate value theorem says that if I were to take any point in between, any height, y, there must be at least one value where f attains that y. So for any y between f of lambda and f of rho, there is an x between lambda and rho such that f of x equals y. Of course, it could be multiple, because maybe my function is like this. But there's at least one. Okay, that's the statement for the initial intermediate value theorem, which we're going to discuss on Monday. And I think that's a good place to stop. Thank you. Have a nice weekend. I'll see you on Monday.